Okay, so algorithms. So what have we learned basically with this very quick review on graph query languages? So there are three things that we need to be doing. So we need to solve pattern matching fast, of course. This is the basic building block. We need to be able to match patterns that also use path. This is not a basic building block, but it's something that's being used often, and where you can see that there is room for improvement. And we need to return and manipulate paths. And this is something which is a bit more obscure, but it's also something which is more challenging. So I'm not going to talk about this last item because we already have a good understanding. So you can start with this paper by Martens and Trautner. Of course, there is a lot of there is a lot to do still, but we're already tackling these problems, and you can read this if you want more information. So about improving algorithms for pattern-based queries, again, so this is the most important part, and the key thing is that relational systems, they don't cope well with patterns. And the reason for this, the main reason for this is that when you translate the graph into a relational database and translate the pattern into a relational query, you end up with something that has a lot of joins. And this is not good for relation systems. They don't know how to deal with this. So of course, if you want to build a graph database system, you have to get around this issue, and every system has their own option. But I'm going to talk today about something that has been studied in the community, but not so much for graphs, and we have not seen it in real systems yet. And this is what we're trying actually. So it's worst case optimal joins. The basic idea behind these joins is that they can speed up queries by opting out of the traditional left deep plan, which is something on the lines of what we have here, opting instead for a different way of computing queries where they start picking node by node on the pattern. So by doing this, you can actually shift from a quadratic algorithm, which is this left deep plan. At some point, you have a quadratic query that you need to store in memory, to an algorithm that works for this particular pattern in the size of the graph to the power of 1.5, which is the AGM bound of the query, the maximum number of tuples that the query could produce. And just a very brief overview of how these algorithms work. So it's this idea of selecting node by node of the pattern. So for instance, we can start with X, and we're going to say, okay, so we will iterate over each possible value of X that we know that could be a candidate answer for this query. So it has to satisfy the pattern below, which is like a sub pattern of the complete thing. For each of these values, we're going to put it in the pattern, and now we're going to look for each node B that is a possible match to Y in the second query. So now we're going to look for all nodes that are connected to A and that can still be answers with respect to the other variables. And we're going to continue like this until we run out of variables. So in this case, at the end, we're going to check for C's that will map to Z in this query where we already have instantiated A and B. So this is the basic idea. Of course, if you want to do this, you need to do it properly. You need some support you need some data structure support. In particular, if you want to implement this on graph databases, you're probably going to end up needing indexes in all relations with respect to both directions of the arrow. So if I have a node, I need to be able to know all the neighbors, outgoing or incoming neighbors, under any possible label, edge label. And there is some more technical things. So you need support for adaptive intersection, which is not necessarily something that systems can normally do. And this is also important. You need to somehow decide that XYZ was a good order for this query, because if we decide, for instance, to start looking for set before, we're going to end up with a similar algorithm, but instead we're going to look for all sets, all values for set, and for each of these values, we're going to produce a new pattern, and so on. And well, this has been implemented in graphs first, and last year for RDF and SPARQL, and it produces quite good results, but they were actually dependent on this good order, and on the particular index structure that the authors of this paper decided to implement there. Which means that there is a huge gap of unknowns that we have no idea yet what works best, what doesn't work, what sort of heuristics can we make to decide good orders, and these are also questions that we really need to answer in systems if we want to start implementing these things. And also from a higher level overview, when we want to issue a pattern over a graph database, there is basically the question of a query plan, and now we have two options. So we can live with both worst case optimal and traditional algorithms together and somehow manage to decide online which is the good option. I'm not aware of any work that has studied that option as well. Or we could just go with a worst case optimal machinery and process everything in a system with this idea. And again, it is not clear how to do this for a graph database system, because you need to start putting more things on top and below. So deciding these things, this is another interesting problem. And again, the data structures that support all of this, we don't know really what works and what doesn't work that much. Also, we need better benchmarks. This is important. Most of the benchmarks are either relational based or are focused on certain particular experiments and patterns and queries that people should do. So here are 2 pointers that have good benchmarks, but this is something that is needed by the community as well. And well, I'm going to stop here, but these are all really exciting questions for systems development. So we have a new sort of backbone for our algorithms, and now we have to manage and decide all the other components so that they play together with this backbone. And I mean, this could be good. We don't really know, of course, whether all of this will actually end up being worth it, but it is certainly something that we need to understand. And for another challenge, now when you start putting paths into this, now this is really getting into unknown territories. So in previous work, we have surveyed that traditional systems, they don't work very well with these sort of queries. Even the most modern ones, they suffer. They suffer with when you start doing patterns, especially complex patterns, and you start putting paths everywhere. This is not an easy query to process. And well, what is the roadmap for doing this? I think that the reason that this is not very well implemented yet is because there are several things that we don't really understand so far. So if we need to understand patterns and paths, first, of course, we need to understand how to compute pairs connected by path. So, which is called the all pair problem for these path queries, right? So I want to find all pairs connected by expression, or if I have one node, I want to find all B's that are connected to this node A via this expression. This is also related to the decision problem. So now I have 2 nodes, and I want to connect whether I want to see whether this node A is connected to node B. And there is also the problem of different semantics, because this really changed for different semantics. So just a small recap, what do we know? If we are talking about arbitrary semantics, the decision problem is very easy. It's just a reachability query. We start in this node, and we need to reach this other node in a way that respects the path. But it gets harder depending on the semantics. So if we start using no repeated something, no repeated edge, no repeated node, what Neo4j uses, then this very simple problem is already NP complete. So luckily for us, there is interesting work here. We have dichotomies and we have tractable fragments. We also more or less, there are also studies that so I don't have it here, but at least, well, Bonifati and authors, they also have this study where they look into query logs, and they really discover the expressions that people were using, and it seems interesting to match them with the tractable fragments from this work. So more or less we know what you can do and what you cannot. But now there is the problem of lifting this into the all pair computation thing. So we know the decision problem. What can we do? What can we say about computing everything? And it's not that easy when we talk about past. So the naive approach, of course, is we're going to check each pair AB of nodes, and we're going to check if they are connected. So if they are connected, we invoke the decision problem. We check if they are connected. If they are connected, this is an answer for the query, and if not, we just continue to the new path. So the question is whether we can do better. This seems to be a very slow algorithm. So right as it is right there, it's already quadratic, not counting the cost that we need to actually check the decision problem. So again, if we're talking about arbitrary semantics, this is already established. I'm going to talk you through this. So the problem of computing all pairs, you can reduce it to checking all possible V's that are connected to a node A, and then iterate over every possible node A. So you would just iterate over nodes on the graph and not over pairs of nodes. So let me be more precise. So if you want to solve for a particular node A, if you want to check all V's connected to A, you need to do BFS over the product of the automaton of the expression and the graph. So you build the automaton for this expression, and now you start in node A Q0. So Q0 is the initial state of the automaton, and then you do BFS, outputting all reachable nodes that look like B and a final state of the automaton. And this way you check all B's that are connected to A. So what is the cost of this? It's vertices plus edges. This is just BFS. It's a standard thing that you can implement. And what is interesting is that this is basically the same time as what it would take for you to solve the decision problem. So you don't really lose asymptotically. You don't really lose much for checking for all nodes instead of a particular node. Which means that so if you go back to the all pair problems, you can do this for every possible node on the graph, and you're going to end up with a more or less with a quadratic algorithm, which is actually much better than the naive approach, because in the naive approach you actually need to do a quadratic number of BFS checks, which is much slower. So this is good for BFS. We have actually tried this in systems, and the approach is quite promising. We were able to beat regular systems in checking path queries. And well, we don't know whether this will be suitable for fitting it into patterns. I'm going to go there in a short while, but let me just say for now that this problem, I have not seen the way to solve this. So we know that there are fragments for which non-repeated sampling semantics is polynomial time with respect to the decision problem. We don't know, or at least I don't know, whether there is an efficient way of actually computing all pairs connected via a path in this expression under no repeated sampling semantics. So this is open, and I think it's an interesting question. So now, but coming back, so we have an interesting way of actually computing the all pair path query problem. We just use BFS. And now the big problem comes when you go back into a system, and now I want an optimal algorithm for this query. I want to actually compute this query. So can we extend worst case optimal algorithms? And just to tease you with the idea of the problem, basically you can think of several ways of actually computing this query. So one possible way is that you start local. So you basically compute all nodes that are friends of each other. And then for each such match AV to this local pattern, the first pattern, you're going to compute all nodes set that you can reach from both A and B. Again, because you can compute the answers for this query by doing a single BFS, what you need to do at the end to actually get the answers of these patterns is 2 BFS per each tuple that is an answer to the friend of pattern, the local pattern. So this is one possible approach. But of course, there is another approach that you can start global. You can actually start computing everything that is a follower, and then check local in that answer. So basically, for each node n in the graph, I'm going to check all AV such that A and B are actually reachable to n. And for each of these pairs AV, I'm going to check now whether they are an answer to the pattern. So what changes here? Well, I'm doing one BFS per node in the graph, which should be less efficient. But then once I do this, I just have to check this local part among all answers from this node n. And of course you can catch it in case you get it for more n's and so on, right? So there are some cases where this could actually be more efficient than the other approach. So we don't know yet, but this is what we're looking for. We're looking for algorithms for patterns and combinations of patterns that somehow can decide when to compute paths right away. So when do you start with the global operations, or when to delay the computation of them, start with local and try to delay the computation of paths as much as possible. So the intuition is that you should be delaying the computations of paths as much as you can, but it's not that clear when you start looking at examples. So again, this is another interesting question that we should be looking at.